a test and like I give you unlimited time, right?
Yeah.
Then because you take advantage of it when you know you don't have it right, you like just focus on it so much, right? And like you fixate on it, you're like, I'm not losing this 5%. But like at the end of the day, it's like it's one thing.
I gave it up.
It is. Okay, so here's our new topic. So you guys get extra bonus functions that twos don't get. But a lot of the properties are very similar. So we're still going to talk about domain and range and input and output and all that other sort of stuff. Only every time we learn a function going forward, there's usually two sides to it. I'll show you what the graph looks like, which some of you already know this is going to be like a V-shaped graph. And we got to talk about some of the algebra that goes behind the function as well. So today there's kind of two halves to the lesson. I'm going to show you how an absolute value works algebraically, and I'll show you how it works graphically. Fair enough?
Cool.
So, some of you in my physics class will actually recognize this, and I'm going to refer to it now that we've actually covered it. On some of the formulas in physics, they put these little like bars on both sides of the letters. You guys notice that yet?
Yeah.
I just kind of ignored it. Just been, no one's actually asked yet.
Wait, which one? Oh, that's the absolute value thing.
Yeah. So the symbol for what's considered absolute value is basically two lines on the opposite side of a value, whether that's a variable, whether that's a number. I think like in physics, like little g gets like lines on both sides of them. So these are not the numbers 1 on both sides. You have to make sure you're very distinctive. These symbols are called absolute values. And essentially the concept is that once in a while, we just don't care if it's negative or positive. That's just not relevant to us. All we care about is just what's just the number. Does that make sense? So if I ask you what's the absolute value of 3, you just say, oh, it's 3. Okay. If I ask you what the absolute value of negative 3 is, then it's just 3. That's the idea. It's like, if it's negative, hey, go to negative. Right? In physics right now, I know not all physics, but for those of you who do get this idea, we've learned this formula of like negative kx. Right? Often my approach to it would be basically, I don't care if it's a negative, just ignore the negative sign. It's not really relative right now. I mean, there is a negative sign because one's backwards, one's forwards, but you get the concept? So sometimes there's a scenario where you just don't care whether it's negative or positive. So that's what this kind of idea talks about here. So I think of it like a number line. If 0 on a number line is kind of dead center in the middle, the absolute value is the distance from 0. So 3 is 3 units away from 0. Negative 2 is 2 units away from 0. So here's even some more examples. The absolute value of 5 is 5. The absolute value of negative 5 is 5. The absolute value of 0, by the way, is 0. That's the only one that's not positive or negative. So this is probably the most important thing that you need to know to do. Here's a way of thinking about the absolute value of a negative number. Mathematically, the absolute value sign is an operation. The way the operation works is it's an if-then operation. Like think computer code. If you see this, this is what you do. So if you see a positive number, leave it. If you see a negative number, add a second negative to make it positive. That's really what absolute value does. If it's a negative number, see how I'm kind of putting this here? The operation really means to add an extra negative sign so that 2 negatives would then make it positive. So if positive x, it stays positive x. If negative x, go negative, negative to make it positive. Does that kind of logic make sense? I'm not maybe writing it as neat as I could, but it's kind of like an if-then statement. Then no. If it's positive x, then make it positive x. Do not. If it's negative x, then double negative. So it becomes positive. Yeah.
So would you use this in like if you're making a graph that can't go into the negatives? That is a logical tool.
Yeah, let's talk about what the graph looks like before we get to the algebra then, just since you asked. This is what the graph is going to look like. Basically, if this was like an XY axis right here, rather than the graph, normally the graph would like say go into the negatives right here. All these negatives values are no longer negative. They now are up here in the positive. Y values, by the way. Does that make sense? these are all negative y values. Well, all these negative y values have now been made to become positive y values.
Do they pretty much just flip on the axis?
Yeah, it's exactly the idea, right? Everything flips on the axis.
It becomes the axis.
Yeah, that's a good way of putting it. This point right here now becomes an axis of symmetry. So you still have an axis of symmetry. This is totally useful, like you can see in like the pool example, right? Where if you want to make a bank shot, you know, if you want to aim over here, then you need to have a nice symmetrical kind of, I don't know, graph to it so that you know where to go for it, right? I have a pool table in my basement I've been trying to learn, right? One of the skills I've learned is that when you want to make a bank shot, you don't actually aim right here. You're supposed to aim like line of sight. Well, actually, sometimes they have like those little diamonds on the side right there. You're supposed to aim like as though you're aiming through the pool table, right? But what'll happen is before it actually keeps going on this trajectory through the pool table, it'll actually hit the rail here and back the other way. Does that kind of make sense? Anything with like lasers or stuff like that in physics where you have like a, you know, it comes in like this and then bounces back as that sort of shape. Let's leave the graphs for a bit though. Let's talk about the algebra part first, because then you guys can answer that question number 5.
Yep.
Okay. So let's do these ones first. These are really basic. If I ask you to evaluate the absolute value of 3, the answer is
3.
Okay. If then statement, you basically said if it's positive, leave it positive. It's positive. Good, we're done. This one will be 7. If then statement, if positive, leave positive. It wasn't positive. Okay, well then what? If negative, add an extra negative. 2 negatives, that made it positive. So this will be 12. What if I do this? Well, you kind of have to approach it, I don't know, like dead mass. What is 2 minus 7? That should have been negative 5. Should have been negative 5. Not anymore. Now we'll make it positive 5. So what would like 3 times negative 5 is what it would have been, right? But now we're going to make it a positive. So 3 times 5 would make it 15. So that would be 5 minus 15 or negative 10. Is it able to follow that? We did like most of that in our heads. 2 minus 7 was minus 5. So I mean it should have been 5 minus 3 times minus 5. But it's not. We're going to make it times like plus 5. We're going to flip the sign around. A lot of kids, they struggle with this concept because they see the final answer of negative 10 and they say, well, I thought you said it could be negative. Well, this portion can't be negative. The other stuff around it could make it negative. Does that make sense? So only the stuff inside the absolute value signs has to be, but it has to be positive. Right. So now for more. Yeah, let's do this. Why not?
Do you treat like the absolute value signs like they're brackets?
Yeah, treat them like they're brackets. So here I'd go say like 5 minus 7, that'd be negative 2. Squared, it makes it all 4. Minus 2 times 4 is minus 8. Add 6, it should have been minus 2. But all of that's in absolute values, so your answer is 2. Does that work? So now here I'm just being mean just because it's me. Right. Absolute value of minus 4 right here means that this should have just been good old 4. This absolute value right here, minus 3, means that should have just been good old 3. 4 minus 3 would give you 1, but that's still inside its own absolute value brackets. But that doesn't matter, because it was positive. So your answer here is 1. Okay, you guys okay with that part so far? Most kids don't overly struggle with just the numbers part. But what happens if x is a letter? Okay, so this is what I need to show you for your assignment. If x is a letter, you actually have to do like I was saying, kind of like an if-then kind of cases. Right? Because we don't know what x is. If x is positive, what do? Nothing. So you'd say like if x is positive, the answer is just x. right? If x is positive, do nothing. Make sense? But if x is negative, then what are you supposed to do? Throw an extra negative in front of it. Then it's going to be negative x. But keep in mind, x is negative, right? So it'll be negative something negative, which would then make it positive. You know what I'm saying? So what ends up happening is you have two cases. So I often write it like this. You have case 1 and case 2. And you actually have to write out two different things because the absolute value of x is either x or it's negative x, depending on the scenario. We're actually not sure which one it is. If it was a positive number, absolute value of x is just x. If it was 2, it's still 2. If it was 5, it's still 5. But if x was negative 5, well then it's negative 5 to make it plus 5. Does that logic make sense? So here's how I like to show it. On this next one here, here's how I'll write this out. It could be just good old x plus 1. Nothing special. If it was positive, it's still positive. But what if the stuff in the absolute value sign was negative? Well, then we just add an extra negative. So it would have been x plus 1. I'm just going to add an extra negative in front of it. All you have to do now is distribute the negative. So it's actually negative x minus 1. Now how we've started to learn in quadratics, there's more than one answer. It's kind of the same thing here. There's more than one answer, but it's a conditional answer. It's dependent on the positive versus negative nature of your answers. If it's positive, this is what it is. If it's negative, this is what it is. So you actually have like two equations kind of combined into one. That makes sense? Okay, so let's try an example. This is kind of like what's on your assignment. Because I think you have ones very similar to this. One I think was linear, one was quadratic. So here's how you go about solving. You have to break it up into like case 1 if it was positive, and you have to break it up into case 2 if it was negative. We don't know the value of x, so we'll just do them independently. In case 1, if it was positive, here's how you solve it. Just ignore the absolute value signs. Then nothing changes. Add 3 to both sides. X is 10. Close that door. That's a generic key for me. Up closer. Actually, no, they don't come closer. Does 10 for x make sense? Oh, yeah. 10 minus 3 would give you 7. If you absolute value 7, it would be 7. We have to do case 2 as well. Here's how I would write out case 2. Negative x minus 3 equals 7. So I've thrown the double negative. If it was negative, the double negative makes it positive. And now to solve this. Negative x plus 3 equals 7. Negative x would equal 4, so x would be negative 4. Does it follow that? Okay, a lot of kids would all of a sudden stop and say, hang on, I can't have negative 4. Well, no, that's not how this works. It just means that our answer is negative 4, but what's what happens when you plug in negative 4 right here? Negative 4 minus 3 would have given you negative 7, but the absolute value sign makes it positive 7. So yeah, it did actually work. So you can have an x value be negative. That's fine. Right? Because you're going to then take that negative value, throw it back in here, and it will then become positive later. So you have two answers essentially. You have one if it's in the positives, one if it's in the negatives. Since I've already talked a bit about graphs already, you know how those graphs are going to have a bit of a V shape to it? Well, if I asked you to graph where it equaled 7, hopefully you can see that you have two locations where it would equal 7. Let's try another one. Over here, do case 1, do case 2. Case 1, literally do nothing. 6 minus x equals 2, minus x equals minus 4, x equals 4. this 4 makes sense. Totally, right? 6 minus 4, 2. On case 2, all you have to do is take the stuff in the absolute value sign and throw a negative in front of it. I'm even just going to start doing more of this in my head. I'm going to make it negative 6 and plus x equaling 2. You see how I just kind of skipped stuff there? X is 8. Does 8 make sense? Yeah, 6 minus 8 would have given you negative 2, but now it gives you 2. Sound good?
Strider and Riley Big Bull and Elia Rothschild. Tyler Archibald, please come to the office. Tyler Archibald, Elia Rothschild, and Strider and Riley Big Bull, please come to the office.
Here we go.
X is positive, you don't touch anything.
Yeah, and since we don't know whether this is positive or negative, we just do both cases. Does that make sense? Because we don't really know what the value of x is going to end up being before we start. Does that make sense? Like, now we know the value of x is 10 and negative 4. Before we started, we didn't know whether it would be positive or negative, so that's why we have to try to do both sides.
But the negative in front of the X is
The negative in front of this x right here?
No.
Or in front of...
The same case.
Oh, right here. No, this negative sign doesn't.
No.
Right? You don't independently make both of them different. Right? Like in case 1, we just left it as it was, the whole thing. In case 2, we just like put a negative in front of both sides. Okay, well that was linear. We can also do quadratics. Honestly, it's not that much harder. It's just using your quadratic skills. So, case 1, do nothing special. X squared minus 3x actually equal 2. So I think this is kind of what you're asking, Naomi. See, there's the negative right here. We don't flip that negative. We just leave it as it is. In the other example, case number 2, it's going to be being negative x squared and positive 3x. You see how this is the case that would have flipped it for us? Alright, now just solve. This will be x squared minus 3x minus 2. And 9 times out of 10, I'm going to give you something nice that you can factor really easily. Because the goal of this is not to make you do like quadratic formula or anything special. So, can you guys figure out how to factor this? It's pretty simple. What did you say? Go ahead. Be brave.
X minus 2. No, I don't think it's x plus 1.
Ah, that doesn't work, does it? Okay. No, this one can't be factored, can it? So this is that 10th time where it actually doesn't factor. Let's do case 2 real quick here. I knew one of them factored. Let's bring this one. We'll come back to this one. Because this one's going to need a quadratic formula. So this one here, 0 would be x squared minus 3x plus 2. I'm just bringing this stuff that way. This one should factor. So give you x minus 2, x minus 1, I think. All that. So then x is 2 and 1. Let's check that.
So I guess x is like 4 answers?
Yeah, it is possible you can have more than 2 answers. You could have 4 answers. Let's just check this one first though. If I put 2 in here, 2 squared is 4. Right. 3 times 2 is 6, so 4 minus 6 would give you negative 2. But negative 2 would then become positive 2. But that's good, right? 1 squared minus 3 times 1 will give you minus 2 as well, actually, but the absolute value is bigger 2, so they still work, right? Okay, this is that extra time where unfortunately it just didn't work out that it factored, so what's it going to be? 3 plus or minus 3 squared, 4, 1, negative 2, all over 2 times 1.
3.56.
So some sort of decimal numbers.
And 1.56 negative.
3 plus the square root, I'll just call it 9 plus 8. Just doing something in my head. Divided by 2. 3.56, that's what you said, right?
Yeah.
I'm just going to play a quick thing here on the calculator just to check my work. I'm going to store that as letter A, just because I want to use that whole value for checking later. And then the other one will be 3 minus root 17 divided by 2. That's one you got, Jake? Okay, and I'll store that one as B, just so that I have it when I want to check my work. So now let's check. If I take A and square it, and minus 3 times A, before I press enter, there's 2 possible answers that'll work. If it equals positive 2, we're good. But if it equals negative 2, we're still good. Yeah, it's positive 2 anyways, we're good. But if it had equaled negative 2, we're good, right? And then B squared minus 3B, so we're good. So there are 4 answers. There was this one, there was this one, there's that one. So now there's a possibility of having more than 2 answers. There's actually 4.
Yay.
So is there ever any more than 4?
Oh yeah.
Oh,
It's also going to be, well, there's actually the possibility there's an infinite number of answers.
so we like go x to the power of infinite.
No. That's actually in the sine graph. You know, in physics we started talking about a sine graph going up and down. If I asked you where it equals this line right here, like say 2, because this graph just goes forever to equal 2 here, and here, and here, and here, and here. So you'll actually have an infinite number of answers. So sometimes I show you how to write what's called a general solution. Don't worry about it, it's not good. Alright, let's try the one last one for algebra, and then after we do the algebra, let's talk about the graphs.
Yay.
Okay, so for this one here, it's 2 cases, right? Case 1. Hopefully you guys would agree with me. This is not a long endeavor usually. You just have to do it twice. X squared plus 4x just equals x squared minus 6x minus 3. Solve. The x squareds cancel. Add 6x to both sides. That's 10x equals minus 3 divided by 10 divided by 10. X is minus 3 over 10. Good. For the other one, you'll have case 2. You'll have x squared plus 4x, but this time it's the negative version of this. So to save time, I'm just gonna flip all the signs, if you guys can follow that, right? So I'll make it a negative x squared, I'll make it a positive 6x, and a positive 3. You know how last time our x squared cancels? Sorry. It should work out to be something reasonably nice most of the time I give you a question. Like the ones on your assignment, by the way, are all easy factorable ones. So you'll have 2x squared minus 2x minus 3 equals 0. Actually, I think this one doesn't factor either. Okay, so all the examples are in my notes don't factor, but I will try to be nice on tests and stuff. So I guess if we hadn't solved this properly, you'd go 2 plus or minus negative 2 squared minus 4, 2 minus 3, all over 2 times 2. No, that's up. 2 plus the square root of, what's that, 4 plus 24? 28? Okay, so one of them I've got here is 1.8228 repeating, something like that. Again, I'm just going to store that to check my work a bit. And the other one is 2 minus the square root of 28 divided by 4. So the other one was negative 0.82287 something. Store as B. The rest are good?
Yeah.
Okay, one last thought. You should always check your work. Because it's possible to get an extraneous solution. just like it was in previous sections. Which kind of stinks going forward. I hate to break it to you, but you should basically from this point on in math, you should always check your work. Because those extraneous ones that like, you get the answer, you didn't do it wrong, but you get like a phantom solution, are always possible. So let's give it a try. I'll use alpha a squared plus 4 alpha a. And I'm going to get 10.614 on this side right here. On this side right here, if I either get 10.614 or the negative 10.614, we're good. So a squared minus 6a minus 3. I got the negative, but that's okay, we're good. So this answer right here checks out. Now for the negative one. So b squared plus 4b, and I just got negative 2.614. I don't actually have to solve the other half, I know this is extraneous. Here's the rationale. I don't care what I type in right here. There is no way that it's going to give me a negative number though. Because by definition, an absolute value should take whatever would have happened right here, and it would make it positive. Makes sense? So when I plugged in my values right here, and I got a negative, that's how you get like your phantom extraneous solution. Is when you do the side that's not the absolute value, if it somehow becomes negative, this thing can't be negative, so then this one can't be negative. So this one right here is not possible. And we should check the last one if you haven't already. So I'm just going to do negative 3 over 10, and I'll store it as c just to make it easier. So we need c squared plus 4c, and actually that one also gave me a negative. So we have a weird scenario here. I actually have 2 extraneous solutions, and only 1 actually valid solution. Sorry. So, just as a hint on your assignment, one of them works nicely, and then the second one you should find extraneous. But I was nice on your assignment. They should all factor, so if they don't factor nicely, you did something. See algebra sound good? Mm-hmm. Okay. This next part should be pretty straightforward. Now I just need to show you how to graph this thing. So this has a graph. Okay. Here's how to find it. If you haven't seen before, go second, catalog, and the catalog literally tells you every single thing your calculator can do. And if you ever want to scroll through the list, I don't have a freaking clue what half of these things do. But this is like literally everything your calculator does, right?
You can clear your entries.
If you wanted to clear your entries, apparently that's how you do it, right?
Where did you get to this?
Second, 0 is the catalog.
And you just click that ABS.
So, but ABS, abs, is absolute value. So, now everyone has a slightly different calculator. Okay. If you have a newer calculator, it might actually put the 2 bars and then like have like a blinky screen.
Yeah, I got that.
There. If you have an older style calculator, you have to like put what's inside there, and then you have to like close a bracket afterwards.
Where is the exact calculator is that? Oh.
So anyways, go to the y equals screen and do the absolute value of x. So either it's going to be abs bracket x, or it will actually look like that.
Okay.
Alright. Anyways, you guys can kind of see how this is going to work. Let's not use that window size then. Let's use this window size. I mean, basically the concept is, here's what the graph would have been. So maybe don't draw this, but the graph of x would have been this, right? That's a good old-fashioned y equals x graph. All your calculator has done is set all of these that are negative y values. It just made them positive. So it's almost like there's phantom solutions down here that would have been there, but they no longer exist anymore because now they're up here. So it makes a nice V. In terms of properties, I think a bunch of you guys have finished the one graphic question on this, right? Like, the properties are the same. X is an element of the reals, because you can type in any value you want for x. For y's, though, it's like a quadratic. This is like a vertex down here. This is a turning point. Sometimes kids have been asking me, why do you call it a turning point? On the little blurb I gave you there, I call it a turning point because not every time a graph turns around is officially a vertex. That makes sense. So this is still that location. This one's just at 0 and 0. So. Your domain would be elements of the reals. Your range would be greater than 0 or equal to it. What else do we do? Your axis of symmetry. It'll be where x is 0 because that cuts it like directly in half. We still don't have asymptotes, by the way. That's our next function. So don't worry about that one. Does that make sense?
Yeah.
Cool. So, picture of pool table, same kind of concept. Anytime that you basically need something to bank or bounce off of something, an absolute value function works. Or, I'm going to go way back to your notes here, just in case you want to try this now. This isn't actually in your notes. Here it was.
Batman.
You want to try to draw Batman?
Right now?
Well, maybe not right now. This will take a while. So you guys can see the equation here?
It's a lot.
Yeah, there's a whole bunch of, but let's talk about why there's absolute values, right? Can you guys see how we have like that, the little pointy sections here? Right? That's how they managed to get a couple of these bits here. They also, it's possible to have a negative absolute value. I want to show you something tricky here. You know how you can have a leading coefficient? If your leading coefficient was negative, it will then make your graph go upside down. The absolute value would force feed something to be positive, but if you put the negative in front of the absolute value, then it forces it to be positive, and then it forces it to be negative. So that's actually how they get some of the stuff down here on the bottom of the graph, is they use absolute values there. Plus, like, these are square roots. So, anyways, one day if you want to try it.
Not
What is
especially,
the
but
SQRT?
I will keep it in.
SQRT is square root.
What do we do in class tomorrow?
Tomorrow's work day. That's like a half-hour-long challenge, I'm sure.
Probably more.
Challenge accepted.
Don't worry. Alright.
We're gonna make one mistake.
And you're gonna end up with this Iron Man one.
Alright, more pool shots, you guys get the concept. Here, let me talk about that leading coefficient then. All graphs have that leading coefficient. If you want to put a number in front of it, it can tweak the graph. So if you put a 2 in front of it, all it makes is the graph becomes twice as tall. You put a 3 in front of it, it becomes 3 times as tall. You put a negative in front of it, it goes upside down, that's all. So, one of the things I'm going to ask you guys to do then over the course of not just this year, but next year, is often you guys have to solve for that leading coefficient. So if I give you an equation, like for example, y equals a absolute value of x, but you know an xy pair, you can solve for the a value. So let's sketch this one real quick. I don't even want to use a calculator.
Please excuse interruption. Kyle Blood, can you please come to the office? Kyle Blood, please come to
Absolute
the
value of
office.
x would normally be your nice little b. What's the negative going to do to it?
Upside down.
And the 2 will just make it steeper, so it's going to look something like this. Alright, love y'all. Alright, that makes sense? And you can graph it if you wanted to, but let's save time. Okay, it's also possible to take an absolute value of a function. This is something a little bit more important for what we're going to do next year in 30, but I want to introduce it now. I could ask you to do the absolute value of bracket x plus 2. I just want to walk you through how this would look then. We're not going to do the table of values, but what would x plus 2 as a graph look like? Well, x plus 2 as a graph would have been this. Right? Good old linear graph. Well, all the absolute value needs to do is where it was negative, it's now positive. So if you actually try to do the graph here now you can kind of check catalog absolute value of x plus 2. Here's another thing I do sometimes. I'll put just the regular x plus 2 graph underneath. And I'll go over here and I'll change the width of the graph just to compare. Okay. And like it literally goes over top of half of it, it's just the other half of this. Let's talk about the quadratic one. So before I absolute value it, what does x squared minus 4 look like? x squared minus 4 should have looked like this. But all of this section down here, I think I have that because it's the negatives. So all it does is it flips it upside down. And this is actually going to look like a W when I'm done. Watch this. Y equals, I'll do one next to it, the absolute value of x squared minus 4. I'll do one, I'll turn this one off. It's a W. It should have gone like that, like a good old-fashioned parabola. But now it doesn't. Okay, if I asked you for properties of this graph, the most unique one of this would be how many turning points are there?
3.
Yeah. You've got a maximum here, and you've got 2 different minimums down there. That's all. So you guys can see why I use the word turning point now, right? Because turning point is pretty generic. This one right here is kind of like a vertex, but these ones here really aren't. These ones are your old x-intercepts, by the way. Whatever the x-intercepts of the other graph are, right? That's what these corners here would be. So here, I'm giving you a graph. What would the absolute value of these graphs look like? Just kind of draw over top of it. Well, this stuff up here in the positive direction, that wouldn't change. The stuff in the negative direction would just look like this, that's all. So there you get your V. Well, most of them would be half of it split off, but And then here's our quadratic. The positive part of the quadratic, it wouldn't do anything special, it would just be where it was. But this little lip that would have went below the axis, it just now goes above the axis. It's some pretty cool shapes in it. You can actually kind of see this is part of like what maybe the Batman symbol is going to require or something, right? It's going to need a little bit of that. Is that good? Alright, what's left? Oh, a picture of what I just showed you. What's that have? Oh, just 2 more graphs. Okay, so let's sketch these ones and then we'll call it a day. So, if you want to, you can just go right into your graphing tab then, right? Now that you know how to do absolute value, just do the absolute value of 3x plus 2. Graph this guy. Oh, look, it looks like a V. Kel shock. You guys feel like you can find all the properties you need? What's the domain?
Next.
Yeah, you don't actually have any issues yet. What's your range? Always, right? Because that's the definition of absolute value. If it goes as low as 0, actually, not always. What if I asked you for the absolute value of a graph that was already hovering above the axis? Well, then it would just continue to hover above the axis. So I guess I shouldn't say that it's always that, but I don't know. Maybe I shouldn't say 9 out of 10. 8 out of 10 does. What are the other properties we need? Degree doesn't apply anymore. Okay. As soon as we start doing things like absolute values, reciprocals, inverses, some of the things we're going to talk about in the next little while, degree doesn't really apply anymore. So don't worry about throwing degree on here anymore. There's a turning point. This is our turning point. So let's see if our calculator can handle this. I'm going to look for the minimum value. And my calculator should be looking for the lowest spot there. Almost like a vertex, right? Ignore the fact that my y value here is something really silly. That sure looks like it's negative 0.6. Repeating probably is what it should have been attempting to do. That makes sense? So sometimes you have to be smarter than your calculator. I don't know why it does this. It's trying to do calculus in the blink of an eye, essentially. But hopefully you agree this value here is negative 2/3 and 0. Which, as I look at the graph right here, doesn't negative 2/3 kind of pop out from the values you're given there, in a way? Right? You throw the 2 on the other side and divide by 3. So there's your turning point. your axis of symmetry, x equals negative 2/3. End behavior, quadrant 2 to quadrant 1. You guys good? One more, I'll call it a day. So here's a quadratic graph. I'm expecting it to look like, I don't know, probably like a W of some kind, depending on what the quadratic looked like before you absolute valued it. So, second catalog, absolute value, the x squared plus 5x minus 6. I'm going to want to change my window just slightly here, if you guys can see, because this point right up here is a little bit too high for my needs. So I'll just change the window real quick and make y go as high as, I don't know, 20. I've been kind of lazy here. I should say negative 10 to 10, negative 10 to 20, and like that. Good enough. Okay, domain, anything. Range, greater than 0. Turning points, I got a couple now. There's one right here, but there's also these ones right here, which, by the way, those ones are your x-intercepts, right? Like your turning points are one and the same with your intercepts. I forgot intercepts last time, didn't I? Oh, you guys probably can figure that out. There's a y-intercept. Where's the y-intercept going to be? Do I need to even use my calculator? Can you figure out the equation? Yeah, I mean, I know there's an absolute value there, right? But it, rather than being negative 6, now it's going to be positive 6. That's all. 0 and 6. Okay, so let's calculate the minimums. You guys won't come to my help anymore. So one of them looks like it's at 1 and 0. Again, ignore the stupid stuff your calculator does at the edges, right? So the minimum way over here. Where the pen is. Probably 6, right? Or negative 6. You know another way you could figure that out? Factor that thing. If you factored that, it would give you x minus 6. No, x plus 6, x minus 1. Alright, if you factored it. Ignore the absolute values, that doesn't really apply right now, right? Well, that'll give you a negative 6 and a 1. Alright, well, that's your intercepts. We do need to know where that point is. That point would have been the vertex of your old graph. So I guess if you wanted to complete the square on this guy, you could. You don't want to complete the square? Okay, I would just use a calculator. So let's just find the maximum. Maximum value at negative 2.5 and 12 and a quarter. Good enough. And I imagine you guys can get all the properties you need, right? The axis of symmetry is negative 2.5 for x. Alright. You guys have any questions? So quick summary of the day. I need you guys to be able to do two things with absolute values. Half of it's the algebraic component, half of it's the graph component. The graphs are probably the easier part. I mean, all you gotta do is just type in the graph and graph the thing, right? Like, now that I've shown you how graphs work, every time we do new functions, all I've got to do is just point out some of the new properties of them, and you'll be like, oh, okay, well, sure, I know how to find this. The algebraic part's probably the harder one, but even then, it's not that hard, right? All you have to do is take your equation, whatever it is, and just do it twice, right? So do case 1 where you just solve it as though there's no signs. Second time, throw a negative in front, distribute the negative, and then solve it again. And when you're done, just check your work. Okay. I'm going to do my best to make sure that if it's quadratic, that you don't have to use the quadratic formula. I'll do my best. Okay? No promises, but I'll My goal is not to test your quadratic abilities, more it's just a test that you get how to solve it. But don't forget to take your answers and go back up and check your work, because they might not actually hold. The rationale as to why they hold is you might have solved for an answer as though it was in the negatives, but the graph actually is in the positives, but for some reason like you seem to think it's still in the negatives, like that like phantom arm kind of thing. You talked about that, where like a guy like loses his arm in the war, but he still feels like it's there. Right? I feel like that's a good analogy. This graph is no longer down here, but you've solved for an answer as though it still was somehow. Okay, you guys good? Okay. What's the plan going forward? Tomorrow's a work day, so try to finish your assignment. The key's already posted. And then next week, I've got you guys, and Bon's gonna take the Dutch 2s for the week, and then we've got more. They've got more. I think we've got a week's worth of work next week, and then the week after that, I think is Monday. It's like work quiz, work day, unit test. So we basically have one more week, and then the week after that's a test week, and then the crazy thing is after that we're in December. Yeah.
Honey.
Sound good? You guys want to keep working here, or you want to go somewhere else? You're fine?
Closer to our lockers.
Fair enough. Okay. Alright, well you guys have the 15 minutes, I guess, to work. So.